In this section, we will examine the relationship between acidity and aromaticity. We notice interesting observations when we compare the conjugate bases of these two compounds. Now, before we begin, since we're talking about acidity, we need to remember an important relationship here, and that is the lower the pKa, the higher the acidity, or the more acidic, the stronger the acid will be. So that is something that I remind you from before. So if we draw the H's on here, it would be these two H's, and this one would have three H's. Very well. So the H's, the hydrogens here, this compound has a pKa of 15. It's incredibly acidic in comparison to this one, which has a pKa of 45. Okay, this is not just 3 times as acidic. This is 10 to the 30. That's how huge that number is. It's bigger than Avogadro's number, 10 to the 30 more acidic. This is the logarithmic scale. So what's happening? Why is this more basic and this is more acidic? For a simple reason is that if you remove an H, and if you recall this, make sure you review that from before, all you need to do is remember to draw the conjugate base is you remove the H, but you keep the electrons. I'm just picking this H, and you keep the electrons behind. So that would make it we'll keep that H right there. So what about this? Why would it be that stable? It's not only resonance stabilized, so this is resonance stabilized, but also aromatic. We already examined this molecule before. And let me go back up and show it to you. Here it is. So those electrons count. So that's why it's very acidic, is because its conjugate base will be aromatic, very stable. However, with this, so we'll just remove one of the H's. So I'm removing this H right here. This one is only resonance stabilized, but there's no aromatic character to it. So that's why this one is more stable, has a lower pKa than the one on the right. It has conjugation, can have a conjugation here, but it doesn't have aromaticity. Very well. When it comes to heterocyclic compounds or heterocycles, they also have interesting acid-base properties. So here we look at the nature of pyrrole and pyridine in terms of basicity. They are how basic they are. So nitrogen containing compounds tend to be basic. Just keep that in mind in organic chemistry. We'll talk about this in chapter 25. So let's draw the lone pairs. There's a lone pair there. And of course, there's a lone pair here. So if we look at the pKa of this one, we have a pKa of the conjugate acid, meaning we add an H, of negative 3.8. It's incredibly basic. It's incredibly basic. And the reason why is because the lone pair, if you recall in Perol, the lone pair is part of the aromatic system. And aromaticity is lost if protonated. So I'll draw this on the side right here. Pardon my drawings. Trying to do my best with this tablet here, but you get the picture here. So we have so if you protonate this, it has a positive. Guess what? This is no longer aromatic, not aromatic. So then the aromaticity is lost, and that means that it's no longer as stable. So that's why it's very acidic, not basic. It doesn't want a proton. This doesn't want a proton. So this is unlikely to form unless you use harsh conditions. Whereas on the other side, this one is a much stronger base. The pKa, let me write it down here. So the pKa of the conjugate acid is 5. And the reason why is because this lone pair, so I'm just going to write LP, lone pair, is not part of aromatic pi system. And it's still aromatic. Aromaticity is not lost. After protonation. So you get the word here. So after protonation, aromaticity is not lost. And therefore, again, that's why it's a much stronger base in comparison. Again, there's no loss of aromaticity. So that brings us to this system or these questions right here. Is this aromatic, non-aromatic, anti-aromatic? What do you think? I mean, it's clearly saying is it non-aromatic or anti-aromatic? So you be the judge. Uh, and try to understand these before we come to class. Look for, again, we already examined this. So we can tell, again, how stable something is based on the pKa. So therefore, this would be more stable because this is aromatic and this is less stable because this is non-aromatic. And so on and so forth. So you might want to think about this. Well, what is this outcome? Is this, you know that this is going to be non-aromatic because it's not a ring, cyclic. But the question is, what would this be? Would it be aromatic or anti-aromatic? And you probably can make a generalization here. You can kind of make a connection. Remember, this class is about really making connections between the different concepts. How come this one has a much higher pKa, which means it's going to make a less stable compound? So determine whether this is aromatic or anti-aromatic and then move from there. And also the same applies here.